All right, y'all. Today we're going to be talking about quadratic inequalities, and we're going to kind of be combining a couple of our prior skills together. We're going to be using those graphing and solving quadratic equation skills we've used before. We're going to use some of those inequality skills, and we're going to kind of elevate that to now solving for quadratic inequalities. So we're going to start with what we know, which is quadratic equations, which when we are solving quadratic equations, we know we are always looking for those x-intercepts or those zeros. So we want to look for where does that graph cross the x-axis? Where is it getting that zero value for y? So we're going to find the solutions to the equation 0 equals parentheses x plus 3 squared minus 4 by graphing. So I'm going to go ahead and graph this. I can use my graphing skills. I know my vertex would be -3, -4. So I can go -3, -4. Pop a nice point right here. And then I know from my standard quadratic graph, I go up and over by 1, and then up and over here. And then I can just reflect those points over on the other side and get a pretty good idea of what that quadratic is going to look like. Does not have to be perfect by any means. And there we go. Nothing too crazy. Okay, so those solutions to this equation, if I wanted to find them, they're going to be those x-intercept or where my graph is equal to 0. So right here, which means my x solutions would be x equals -5 and -1. Nothing too crazy. We can also, of course, write them as -5, 0 and 1, 0. We can write them as points as well. Sorry, -1, 0. Okay, so that's pretty simple. We've done that before. We've used our graphing skills. We've solved quadratic functions. Okay, now we want to elevate it to solving a quadratic inequality. And the key with solving a quadratic inequality is that instead of it just being a specific value, it's now going to be an area or it's going to be a region. Okay, we're not just finding those x-intercepts or zeros. We're finding that region where I'm going to get that 0. Okay, and how this is going to change, we're still actually going to be looking for and trying to identify some of those zeros, but this time instead, we're going to be looking for is my whole graph above or below 0, not just those points where I'm equal to 0. Okay, so we have the exact same graph, so I can just copy my graph over to the other side. Okay, and what's important here is that I have those same solutions. And what you notice looking at our graph is at those solutions, at those x-intercepts, my graph actually crosses the x-axis. So it starts in positive values, then it goes to negative values, and then it goes back across to positive values. So what I'm going to do is I'm going to actually add in some dotted lines to represent where those intercepts occur. And you're going to see this is going to break my graph into 3 different sections. The section of x values that are less than -5, the section of x values between -5 and -1, and the section of x values that are greater than -1. And what I'm looking for is I'm looking for solutions to the equations that 0 is greater than parentheses x plus 3 squared minus 4. Now that can be a little confusing to read. So anytime we see an inequality like that, we can actually flip it around so that it makes a little bit more sense. So I'm going to shift my equation to the other side. X plus 3 squared minus 4. And if it's 0 has to be greater, then this has to be less than 0. So when I literally say flip, I mean flip the entire equation around. It's the exact same thing. So I'm looking for when this equation is less than 0. So looking at my graph, where is that equation less than 0? Well, definitely here in the middle between -5 and -1, this shaded region here in the center. And so that is my answer. It's really simple as that. And the way that I can represent this shaded area is with our inequality notation. So I can say x values that are greater than -5 but less than -1. And that's really all there is to it. If I wanted to instead, I could also use interval notation, and I can say -5 to -1, and that would be the exact same answer. So you can use interval or inequality. I'm going to use them kind of interchangeably as we talk today. Okay, so that's all we're doing. I want you to notice the big difference between the first one when we did it for equals and the second one we did inequalities. For equals, we're finding those x values, those specific solutions. For inequalities, I'm finding that region, that area where my graph is actually going to be above or below that 0. Okay, so let's look at another example. So example 1, we want to solve the inequality x squared minus 2x is greater than 3 by graphing. So right now, if you notice, difference from what we just did, we don't have one side that is equal to 0. So I'm going to move that 3 first. So let's -3 to both sides. So it's going to give me the new quadratic equation x squared minus 2x minus 3 is greater than 0. Okay. And you might kind of think, I don't really know how to graph that, but remember, we have some tools. We can keep it here in standard form, although that's not super useful, except it would tell me where my y-intercept is, which is here at -3. Okay, but I could also get this into factored form. So if I wanted to factor it, factors of -3 that add up to -2, that would be x minus 3 and x plus 1, which would be greater than 0. So now that I have this in factored form, I know that I have the two factors of -1 and +3. And once I have that, I could find more things. Like I could see pretty clearly that my axis of symmetry should be at +1, halfway in between -1 and 3. Okay, but I really don't need anything more than this. I have everything I need to be able to solve my inequality. Because remember, all I need is where that graph crosses 0 so that I can split it into my regions. And you're always going to have these 3 regions for these quadratic inequalities. Okay, and so now I'm looking for where is this quadratic function greater than 0, where it is greater than 0 in 2 different places. Here for values less than -1, and here for values greater than 1. So those 2 regions are going to fall in for my quadratic inequality. So I can write it either as 2 separate inequalities, so x values that are less than -1 and x values that are greater than 3, or I can write it as 2 separate intervals, -infinity to -1, in union with 3 to infinity. And we haven't seen this U sign before. It means union. It's kind of a fancy way of saying and in mathematics. We use it when we do interval notation. For some reason, we don't typically use it when we do inequality notation. It usually only shows up with interval notation, but you could technically use it with inequality as well. But any combo of these answers would be fine. We just want to make sure that if we do have 2 regions that solve the inequality, that we are getting both. Okay, so go ahead and pause real quick. I want you to do the exact same thing. Okay, same exact equation, but this time the inequality is slightly different. So see if you can come up with the answer for that second piece. All right, on this one, we do have that exact same equation. This time it's less than or equal to, so we're looking for where is that quadratic function below that x-axis, which is definitely going to be in that center region. Big thing, it is less than or equal to, so we have to make sure we include those equal to signs if we're doing inequalities, and of course, if we were doing intervals, we would use brackets on the edges instead of parentheses. So super, super important thing to note. Okay, so to kind of put it into perspective of what we are trying to actually do, for each of these inequalities, the first thing we want to do is we want to change the inequality to equal 0 and then solve to find those x values. Once we have those x values, we can graph it, but sometimes a graph is a little difficult. So I'm going to actually show you a more straightforward method. We're just going to plot those x values on a number line because I already know that those x values are going to be where my quadratic function switches from above or below that value of 0. Okay. And on that number line, we're going to do an open circle if it represents a less than or greater than sign, and a closed circle if it represents a less than or equal to or greater than or equal to. Same thing we're used to. Okay. Then instead of actually fully graphing, which you can graph if you kind of know what the shape of the graph is, but if you don't know what the shape of the graph is, we can actually do some test values on the interval and plug these values into the inequality to determine if the segment should be included, if it's going to be above or it's going to be below. And then we're going to write our solution as an and or an or statement. So either it's this one and this one, or it's this one or this one, depending on what values we actually get into our graph. Okay, so let's look at an example for this. So number one, we have x squared plus 3x minus 18 is greater than or equal to 0. So our first step has already been done for us. This one is already set up where our 0 is on one side of the inequality. So we're going to go ahead and move on to our next step, which is to go ahead and factor this. So we can factor x squared plus 3x minus 18, factors of negative 18 that add up to 3. That's going to be positive 6 and negative 3. So our step 1 is going to be to factor this into x plus 6 and x minus 3 are greater than or equal to 0. Okay, which is going to give us the 2x solutions. Of course, we can take those factors, set them equal to 0 of x equals negative 6 and x equals positive 3. Okay, so once I have those solutions, then I move on to step 2. Which step 2 is to go ahead and make a number line. So for my number line, I'm going to plot those points. Well, we were going to plot those points on there. So I'm going to plot those points x equals negative 6 and x equals 3 onto our number line. Because it is a greater than or equal to sign, I'm going to use closed-in dots for each of them. To represent that we are actually equaling these values. Okay, so negative 6 and 3. Okay, and then to help show that separation, this is our 3 little regions, negative 6 and 3. So from here, if you can visualize the graph of x squared plus 3x minus 18, which a lot of you might be able to, you can just kind of sketch that graph in and use the shape of that graph to determine which of these should be above and which of these should be below. If you can't quite visualize the graph, an extra way that we can check is we can actually do some test values. And we're going to do that real quickly here. So for step 3, on each of our intervals, which you can see that we clearly have 1, 2, 3 intervals, we're going to plug in an x value that fits on that interval. So for my first interval, values less than negative 6 would be like x equals negative 7. Between negative 6 and 3, you always want to pick something pretty easy. So I'm going to pick 0, x equals 0. And then greater than 3, x equals 4. You, of course, can pick any number on the interval, y'all, but remember you have to plug it in, so we want to keep it pretty simple. Okay, so plugging in those numbers, x equals negative 7. That's going to give me negative 7 plus 6. And negative 7 minus 3, which would give me negative 1 times negative 10, which would give me 10, which is positive. I'm going to go and add that onto my number line up here. Okay, then plugging in 0, we would get 0 plus 6 and 0 minus 3, which would give us 6 and negative 3, which gives us negative 18, which is a negative value. So I'm going to plop in a little negative right there. And then last but not least, plugging in 4, we would get 4 plus 6 and 4 minus 3, which would give us 10 times 1, which equals 10, which is once again positive. and we can plop in a positive. And what that positive does is it tells us what the shape of our graph should actually be, which is positive means above, negative means below, and positive means above again. Okay, and then going back to my inequality, I'm looking for values that are greater than or equal to 0. So for values that are greater than or equal to 0, that's going to be values that are positive or above that number line. So that's going to be here and here. So for my final answer, I'm looking for values less than -6 and values greater than 3, including both. That's why I did the closed-in dot. So x is less than or equal to -6, and x is greater than or equal to 3. Or, of course, we could do -infinity to -6 with a bracket in union with bracket 3 to infinity. Remember that bracket represents that including if we want to do interval notation instead. So either of those would be perfectly fine. Notice we didn't have to graph on this one, but of course, if you kind of know the shape of the graph, which looking at a positive x squared, we know it's going to open up. So we pretty much already know what that shape is going to be. If you can visualize the graph, you don't have to do the extra plugging in step. If you can't visualize the graph, you can always use that. Okay. So using what we just learned on A, go ahead and try and solve B. Okay, I'm just going to ask you to solve B for right now, so go ahead and pause me and solve B. We'll talk about B here in just a moment. All right, let's talk over our work here on B. So 4x squared is less than 25. We have to do that first step this time because we do not have 0 on that right side of our equation. So we can subtract 25 from both sides. So we get 4x squared minus 25 is less than 0. Now, last time we had an a equals 1 quadratic. This time we have a difference of perfect squares quadratic. So that's going to factor into square root of the first term, square root of the second term. 1 is a subtraction and 1 is addition. So square root of 4x squared is 2x. Square root of 25 is 5. So we get 2x minus 5 and 2x plus 5 are less than 0, which is going to give us the two factors of positive and negative 5/2. Okay, so plotting that on our number line, negative 5/2 and positive 5/2. Once again, if you can understand that shape, this is a positive 4x squared minus 25. You can just sketch in that graph right away. If you can't think of the shape, we of course can plug our test interval values in. I chose -3, 0, and 3. You could choose something different as long as it is on that test interval. And you should have gotten positive, negative, positive. And then of course we want values that are less than 0. So that's going to be that middle interval where our quadratic dips down below. So -5 is less than x, which is less than 5/2, or of course parentheses negative 5/2 to 5/2 parentheses. Okay. Hopefully super straightforward on B, very similar to A. We just use a slightly different factoring method at the very beginning to get this one set up. Okay, so let's pivot a bit and let's do C. C is going to be a little bit different. Okay, so on C, we have 2x squared minus 4x minus 5 is less than or equal to 0. Okay, and this isn't A is greater than 1, so we're looking for factors of that a times c term that add up to b. So if we do our a times c, 2 times -5 would of course give us -10. So we're looking for factors of -10 that would add up to make -4. Now the only factors of 10 are 1 and 10 and 2 and 5. So that's going to leave us with 1 and -10, -1 and 10, 2 and -5, and -2 and 5, which of course one of these has to be negative because of that -5. And then of course we want these to add up to -4. Now looking across those factors, y'all, none of those are going to add up to -4, which tells us that this actually isn't factorable. We cannot factor this using traditional means. So when we can't factor by traditional means, but we still need those x solutions, because remember, we are just factoring so we can get those solutions, those zeros. We always have a trusty method that we can use to solve for our x values, which is our quadratic formula. So let's go ahead and use our quadratic formula for this one. It's a little bit grosser, but it's going to give us those x solutions we need. So x is equal to We don't need to be in green. X is equal to negative b, so negative 4 would be positive 4, plus or minus the square root of b squared, so negative 4 squared, minus 4 times a times c, and then all over 2 times our a term. Okay, solving from here, we would get 4 plus or minus the square root of 16. Negative 5 times 2 is negative 10. Negative 10 times negative 4 is positive 40, all over 4. Simplifying a little further, 4 plus or minus the square root of 56 divided by 4. I can split that 56 into 4 times 14 over 4. Square root of 4 would give me 2, so 4 plus or minus 2 square roots of 14 over 4. And you might be thinking, Mr. Arbone, we could split 14 up some more, like into 2 and 7, but 2 and 7 are both prime, so I'm not going to be able to pull anything else out of 14, but I can simplify this. 4, 2, and 4 are all divisible by 2, so that would give me x is equal to 2 plus or minus the square root of 14 divided by 2. And of course, we could leave it like that, or we could simplify it to x is equal to 1 plus or minus the square root of 14 over 2. Either way would be fine. Okay, so now that we have our x solution, okay, or x solutions, I should say, because it's plus or minus, we have everything we need to go ahead and set up our number line. Now, I know you might be thinking, Mr. Arbone, that was so much work, and I don't disagree, okay? But we're going to go ahead and draw on a number line, and on that number line, we're going to do closed in dots, because this is a less than or equals to. And one of them is going to be 1 minus, because that should be our smaller root, and the other one is going to be 1 plus. Okay, and from here, if I wanted to, I could plug in numbers in between. So definitely 0 would be a safe number in the middle. On either side, you might not know, so square root of 14 divided by 2, and then subtracting that one from 1 or adding that from 1. So you might want to go a little bit bigger on numbers if you need to do test values. Or, of course, if you feel comfortable, we can go back to our original quadratic function, positive 2x squared. That's going to be an up opening quadratic. So we pretty much already know, and by pretty much, I mean we do already know what the shape of this quadratic function is going to be. So knowing that that is our shape and knowing that these are our 3 regions, we're looking for values that are less than or equal to, and less than or equal to is going to be this region right here in the middle, which of course, if we get that region right there in the middle, then that will get us our inequality. So 1 minus the square root of 14 over 2 is less than or equal to x, which is less than or equal to 1 minus the square root of 14 over 2. And of course, we could do the exact same thing in brackets. So bracket 1 minus square root of 14 over 2, 1 plus square root of 14 over 2. So this one's a little gross, but really the only thing that's changing from A to B to C is that slightly different factoring method. So you might notice really the most important skill here is being able to factor to be able to find those x solutions, because once you kind of get there, most of these are pretty similar in those final few solving steps. Okay, go ahead and pause me again and solve D. Okay, once again, D, you're going to have to get everything onto one side. And the factoring on this one is a little bit challenging, but I think y'all can do it. Okay, so go ahead and pause me and see if you can do D on your own. All right, let's go ahead and talk through D. So we have negative 1/2 x squared minus 6x is greater than 16. We want to get that 16 to the other side, so we have to subtract it. So we get negative 1/2 x squared minus 6x minus 16 is greater than 0. Now from there, we could factor it as is, negative 1/2 x squared minus 6x minus 16. But that's a pretty gross function to factor. We, of course, could do our quadratic function if we wanted to, but once again, that's going to be a pretty gross quadratic function to do. But we can actually make this a little simpler. If you notice this -1/2 here in the middle, I can get rid of it if I just multiply everything by -2. And of course, if I multiply one side of the equation by -2, as long as I multiply the other side by -2, it's still equivalent. Same thing applies for our inequalities. So multiplying the left side by -2, that's going to give me positive x squared plus 12x plus 32. And then on the other side, 0 times -2 stays 0. But important note, if we do multiply our inequality by a negative, then it's going to flip that inequality sign. So instead of it being greater than 0, this now becomes less than 0. So just like it changes the sign of all of our numbers, it also essentially changes the sign of our inequality. So factoring that, it factors into factors of 32 that add up to 12. So +4 and +8. So that gives me the 2x factors of x equals -4, x equals -8. Popping them on my number line with open circles because I cannot equal -8 or -4. And then, of course, my shape. Now, I know my original was negative, but the graph that we're actually working with is this positive one here. So it's this positive x squared plus 12x plus 32. And then I'm looking for values that are less than 0. Once again, I'm using my new equation, not my original. And that's going to give me this region in the middle. So our x values are from -8 to -4. So the actual solving inequality parts, y'all, is pretty straightforward. Most of what we're doing in this solving quadratic inequalities is really utilizing those solving quadratic skills that we kind of honed back in Unit 1B. But this is going to take some practice, so definitely hone in, do some of that practice today, do some of those activities, and I'm sure you're going to get a little bit better.